So it turns out that matrix-matrix multiply over the decades has been the topic of intense research and continues to be so. Now think about that for a second. We're computing C is equal to A times B plus C. If you look at a typical entry here, the ij entry in C, that is equal to the dot product of the ith row with the jth column added to that entry. These two loops here loop over all of the entries in matrix C. And then this loop right here, what we call the innermost loop, performs the dot product. Okay? And you can actually rearrange these loops in any order you want, which means you have 3 choices for the outer loop, 2 choices for the next loop, and then 1 choice for the last loop, so that there are actually 6 ways of arranging this. That's called reordering the loops. Okay, so it's all about how to optimize a triple nested loop with one assignment statement in the middle. But it turns out that that's not what it's all about. It's actually all about trying to make sure that the data movements that happen between the layers of memory are performed in such a way that they don't get in the way of performance. Now, gosh, around the turn of the century, I was visited by someone who then became my colleague, whose name is Goto, whose algorithm now is actually at the core of, from what we know, just about every high-performance implementation out there. And he released his implementations as part of a BLAS library called the Goto BLAS, and the algorithm we tend to refer to as Goto's algorithm or the Goto BLAS algorithm. Okay, and what it's all about is slicing and dicing. Okay, now, how does this work? Well, you start with a matrix-matrix multiply in main memory. Okay, C, A, and B. Okay, now, typically these matrices are too big to fit in the L1 cache. You can't just go read them, do a bunch of computation, and write the result back out. So what do? Well, you've learned that a matrix-matrix multiply can be broken down in terms of smaller operations. Now, you could say, well, let's just do it as a sequence of matrix vector multiplies so that we just run through all of those. Well, but you've learned that if you do a matrix vector multiply, if the matrix is too large to fit in the L1 cache, then you're still going to have to do a lot of data movements, and that's not a good idea. That's what led us to blocking. And it turns out at the outermost level, you end up blocking B vertically, which was one of the algorithmic variants that we systematically derived. Okay, then what happens? Well, none of this fits in the L3 or L2 or L1 cache if these matrices are large enough. So you end up blocking some more. The algorithm that partitions in that direction is actually the algorithm that in the picture over there is the outermost loop. Okay? So the next level down, we now are left with a problem of this size. And what we do is we go and we partition A and B in this direction right here. What did we notice if we partition A and B so that we march through the matrix A by columns and B by rows? We ended up with an algorithm that cast most computation in terms of a rank K update. Okay, now the purpose of the game here is to do these partitionings in such a way that this block actually fits in the L3 cache. Okay? Now, we then tend to say, and then you move that block into the L3 cache. Well, there are no computer instructions that say, move this into the L3 cache and tie it down there until later. But what you can do is you can arrange your computations in such a way that how data is brought in by the hardware into the L3 cache and how it's evicted when the L3 cache fills up, that mechanism will tend to keep this block in the L3 cache. Okay? But we're just going to think of it as we're moving that block into the L3 cache. So, that's what we have next. So notice that now we're really thinking of doing this operation right here. That's the next level down. Okay, so then we go, let's make this a little bit bigger. Now we're down to having to do this times that as part of a bigger problem. This actually is now quote unquote in the L3 cache. And at the next level what we do is we partition A into blocks like that, and then we arrange the computation in such a way that a block of A ends up staying in the L2 cache. Okay? Now, if you do that, then you need to take matrix C and partition it into row panels as well, because that's one of the algorithmic variants we saw. It's the one where A gets partitioned and C gets partitioned. Okay? Then what? Okay, then we take this data that is now quote unquote in the L3 cache and we partition it into smaller blocks. And the idea being that this block has to be updated with this times that, which is now this times that. If we partition this into smaller pieces and this, that's again one of our algorithmic variants that we came up with. And now you can take this times a typical block over here to update a typical block over there. And this typical block here then ends up being brought into the L1 cache. Again, the computation is organized in such a way that the mechanism for replenishing what is in the L1 cache encourages this data to stay in the L1 cache. Okay? So now we're left with having to do this times that to update a little sliver of C right here. Hopefully you're following along with how the loops develop over there on the right. And for that, we end up doing what? Well, we do what we do well. We partition again. And how do we partition this time? Well, so then it turns out that you end up partitioning matrix A into little slivers, and then you end up with tiny little blocks of C which actually fit in the register. So this is now, say, a very tiny block of C, maybe a 4 by 4 block of C. Okay, and what you need to do with that little block is do a tiny matrix multiply of a 4 by something matrix times a something by 4 matrix to update that 4 by 4 matrix. Okay, so what we have now done is we've brought our matrix multiply down to a little tiny block of C that, for example, would be a 4 by 4, but how big that block actually is depends on how many registers you have. That is updated by a little sliver of A and the sliver of B. So that's still a small matrix-matrix multiply. We've been slicing and dicing, doing matrix-matrix multiplies all the way up the chain here. How is that implemented? That is actually implemented by viewing the little sliver of A as a bunch of columns, the little sliver of B as a bunch of rows. And what did we learn when you do this one column and one row at a time? You end up doing this times that plus this times that plus this times that. Every one of those is a small column times a small row. That's an outer product. So at the very core of everything is a matrix-matrix multiply implemented as a sequence of rank 1 updates to update a tiny little matrix. So at that point, you end up actually doing a matrix vector operation, a rank 1 update. But the key is that the data with which you then do that rank 1 update, part of it is sitting in the L2 cache, part of it is sitting in the L1 cache, and it turns out that that's fast enough to be able to do the computation, to be able to feed the computation with data so that you can get almost peak performance out of the processor. And it's that tiny little bit that we in our research group then assembly code. So we've brought it down to a tiny little unit that actually needs to be highly optimized and needs to be specialized for an architecture that happens to come along. Okay, so hopefully this gives you some idea of how this slicing and dicing fits in. Now there's a key insight here. This tends to be the algorithm that performs best, and there are theoretical reasons why this particular algorithm performs best. Now, if you think about it, even if you gave something that is a rank K update, where this size here is the magic size of what you want to put in the various caches, even if you do this algorithm with a matrix-matrix multiply that has that shape, this rank K update shape, it turns out that the algorithm executes at peak performance. And what does that mean? That means that when you derive blocked algorithms, and when you are on the lookout for which algorithm to then pick, it is the algorithm that casts computation inherently in terms of rank K updates that you would expect to actually give the best performance. It turns out that a rank K update is also relatively easy to parallelize, which is very important on current architectures, but let's not get into that.